All right, action.
All right, everyone. So what we're going to do in this lab is we're going to verify the law of conservation of energy, okay? And we're going to do that by dropping a little pipe through a hollow aluminum tube. So we're going to measure the potential energy and kinetic energy of this little pipe as it falls through the big pipe, okay? So let's take a look at this setup real quick. So this is just a hollow aluminum tube, and these three little devices right here are timers. They're photo timers. So what they do is they simply measure the amount of time that the little pipe, as it falls through the tube, blocks a little beam of light that shines through here. So in here, there's a hole in this tube, and this little infrared light shines through the tube. And then these timers right here are going to simply measure the amount of time that this little pipe blocks them on their way through as it falls. Okay? So we need to figure out what the potential and kinetic energy is at all these locations, at the very tip top of the pipe, at the top photo gate, the middle photo gate, and the bottom photo gate. And then ultimately, we're going to try to figure out what happened to the energy when the pipe hits the ground, okay? All right, so let's kind of review potential and kinetic energy. Conceptually, we know what's going to happen here, right? As I'm holding this pipe, I'm suspending it, what kind of energy does it have? It's not moving, but it's above the ground, so it has only potential energy, right? But as I drop this pipe, that potential energy is converted into kinetic energy, right? And the further it falls, the lower its potential energy gets. But what's happening to its speed? It's increasing, right? It's accelerating at 9.8 meters per second squared. So as this little guy falls, it just goes faster and faster. So its kinetic energy increases while its potential energy decreases. If we add the potential and kinetic energy together at any of these locations, we should get the total energy of this system. It should equal the maximum amount of energy that we calculated at the very top of the pipe, okay? So we're going to verify to see if that really works or not. So how are we going to do this? Well, let's take a look at the potential energy formula up here on the board and just kind of review what these variables are. So the M is going to stand for the mass. And remember what we're doing is we're talking about this little pipe right here. Okay, that's the object in question. So it's going to be the mass of the small pipe. And what are the units that we use in these formulas? They're all going to be in kilograms. Okay, all right, so we got to make sure it's in kilograms. The only problem is the little balance that we're about to use isn't going to give us a mass in kilograms. Let's find out what it is. So let's take a look at the balance here. This is a centigram balance. So it's going to give us the mass of this little pipe down to the nearest hundredth of a gram. Okay, it looks like it's 31.60 grams. Let's write that up here. 31.60 grams. We don't want grams, we want kilograms. So how are we going to change this into kilograms? Well, kilo means 1,000, so there are 1,000 grams for every 1 kilogram. So how are we going to do this? Well, here's the math that we're going to do. We're going to set up a little ratio here. We know that for every 1 kilogram, there are 1,000 grams. So what I'm doing is essentially taking 31.60 and dividing by 1,000. And look what happens to the units. grams are going to cancel, and I'm going to be left with the units that I want, which are kilograms. Now feel free to plug this into your calculator. You could do that if you need to, or you could just say, wow, I'm dividing by 1,000, so what does that do to the decimal? Which way am I going to move this decimal, and how many places am I going to go with it? Since I'm dividing by 1,000, there are 3 zeros here. I'm simply going to move my decimal point 3 to the left, okay? So what this is going to equal is 0.03160 kilograms. That's kind of the beauty of the metric system, right? So that is going to be the number that we use in both the potential and kinetic energy formulas, okay? All right, so now we've figured that out. We've got the mass figured out. Now it's about this guy, little g, which is the local acceleration of gravity. We are here on Earth, so that number is going to be 9.8 meters per second squared. That's a constant, so we don't have to worry about that. You just have to know that it's 9.8 meters per second squared. And then finally, the h stands for height, and that's going to be measured in meters. The height of what? Well, it's not going to be the length of the little pipe. It's the height above the ground. And that's where we're going to need to measure the height from the ground to these different photo gates. Okay, the lower, medium, top, and actually the top of the tube as well. Okay, so let's try to do that. Again, we're going to be using the metric system again, and we're going to be using these big meter sticks to calculate the height. Okay, so this is 1 meter high right here, and the top is 2 meters. So anything below this is going to be 0 point something meters tall. Okay, so remember, we have to use meters. We can't use centimeters. We can't use millimeters. But we want to get a measurement down to the nearest millimeter. That is the nearest thousandth of a meter. And if we look closely at this, we can see that we have these little lines scribed on here. These guys right here, where you see a 40 and a 50 and a 60, the difference between here and here is 10 centimeters, okay? So it's a decimeter. Now these little guys right here, the 2, 3, 4, 5, 6, 7, those are centimeters. There's 100 of those in every meter, okay? And then there are 10 little tiny lines in between each of the centimeters, and those represent, you guessed it, the millimeters, okay? So these represent 1,000th of a meter. In other words, 3 past the decimal, okay, when we're measuring this. So let's take a close look at this bottom measurement here. Actually, yeah, let's do that. So I'm just gonna put this guy up here, and then I'm just gonna carefully look at the bottom and go, okay, well, this is 1/10 of a meter, 2/10, 3/10, here's 4/10. So my number is going to be 0.3, and then I look at my centimeters, right? The hundredths of a meter, and this is going to be 3.1, 3.2, 3.3, 3.4, 3.5, 3.6. I'm sorry, 0.36. So 0.3, 0.36 is right there. So it's a little more than the 6. So now what I have to do is count how many millimeters past the 6 I am. And so what does that look like? It looks like there's 0.365. Looks like a 6. What do you think, Rusty? Second opinion?
I'm not sure.
Okay, we're gonna go with a 7 right there.
We have it on photos.
We do have photos that are close up as well, so you'll be able to take a look at this in more detail. But this measurement is going to be 0.367 meters tall. So let's just go ahead and write that up here. So lower photo gate. Lower photo gate equals 0.367 meters. Okay? All right. Okay, so that's all there is to measuring. But let's do it again. Why? Because this is tricky and it's easy to make mistakes. Let's take a look at the middle photo gate and let's try to look at how we're going to measure this. So I've got it set up here. First, I want to make sure that the measuring stick is vertical, not at a slant or anything like that. And then I'm going to look over here and I'm going to see that this is 1 meter. So the middle photo gate is still less than 1 meter high. So how tall is it? So this is 0.7, this is 0.8, this is 0.9. So it looks like it's just a little bit less than 0.9 meters high. So what is this? This is 0.8. This is 0.89 right here. 0.89, and then it looks like we might be 1 or 2 past in terms of millimeters. Again, this is going to be a photograph that you can blow up. It's really high def, so you can see the details here, okay? So we've got 0.89, and then looks like maybe 2. 0.892 meters for that one. So middle equals 0.892 meters. All right. So let's take some data for the top one. This is where you guys get to figure this one out. This one's a little tricky though because it's over 1 meter off the ground. So here's the 1 meter mark. So it's a little bit tricky. Looks like this thing, yeah, let's flip it around. So there's our 1 meter mark. 1.1, 1.2, 1.3, 1.4. So it's less than 1.4. What is it? 1.38. And then you want to count those millimeters, and that's going to give you the value down to the nearest thousandth of a meter. So it looks like it's probably 1.386 or 7. Again, you're going to want to look that one up and on the picture and figure that out. And then finally, the last thing we want to do is measure the overall height of this thing down to the nearest meter. And I'm going to need to grab that ruler. Let me grab this really quick. This is going to be the easiest way to do this. So here, let's take a look at the very tip top. I'm going to put this on here just to give me something to measure to. So there's the 1.5 meter mark right there. Looks like it's 1.54, and then however many millimeters come after that, looks like maybe a 7 or so. So it looks like 1.547 possibly. Okay? All right, so we've got the height all figured out. I'll let you guys figure out the top and the middle. But this is all we have to do for the potential energy. Now that we have these numbers, we know the 9.8, we know the mass of the small pipe, all we do is multiply these together and we get a value. Let's just do one to make sure we're on the same page. So let's look at the lower photo gate and try to figure out what the potential energy is there. So I'm going to take This number, 0.03160 kilograms, multiplied by 9.8 meters per second squared. And then I'm going to multiply that times the height of the lower one, and that's 0.367 meters. We're going to multiply that together. We're going to get a number that has the units of kilogram meters squared per second squared, which is a joule. So remember, joules are going to be your units for any measurement involving energy. Okay? Right, so that's pretty straightforward. So potential energy, easy. We take those little measurements and we're good to go. Kinetic energy, though, is a little bit different. So over here, let's look at the kinetic energy formula for a minute.